Okay, well, good evening, everyone. Welcome to the November meeting of the RASC Ottawa Centre. It seems like it's like the July meeting with the temperature we're having, so I'm glad. Great turnout tonight, by the way. So thanks for you all coming. We have a terrific meeting, as you'll see, and a terrific agenda. Not just our main speaker, but every speaker and every presentation you'll see is really special tonight. Next slide, please. So here's our agenda tonight. We have to do a procedural thing. Gary's going to talk about our center, our one of 28 centers across Canada, and we have a council and we have elected members and so forth. And Gary's we have to go through this process once a year, and Gary's going to talk a little bit about that. And it's a more lengthy process in the December meeting, but Gary will give an update. Our main speaker is Ivan Semeniuk. And I'll be talking about Ivan in a second, so I'm really delighted that he's here. He'll speak for about an hour, okay, or about 50 minutes, and then we're going to have about time for 5 to 10 minutes of questions. Then we're going to have a short break. I'm sure you noticed as you were walking in that we've got some telescopes set up for a display in the corner here. Also, when you walked in, you probably most of you picked up a door prize ticket. If you didn't, we're going to have them available for you to pick up at break time. And then, of course, at the end of the meeting, we're going to do a draw I got a ton of door prizes, and I really don't want to take them back in my car tonight. So we're going to try and lighten up my car. There's some really nice ones, some very, very generous members. It's going to try and be about a 10-minute, 15-minute break. We'll see how it goes for time. After that, Al Scott will give an astronomy news update, things that are timely in our area of interest. What to expect in the night skies for the month of November. That's Dave Chisholm. Dave is also going to talk about a tour they took recently, a very special tour for Dave, and I think it'll be special for us, of the Algonquin Park Radio Observatory that I think many of us have heard of, but probably many of us haven't gone to it. I'm going to bet. We've got some of the finest astro images and videos, I think, of the year tonight. So while that's at the end of the meeting, you don't want to miss it. Okay, and I suspect it's going to be just awesome to see on this screen with our high resolution projector. Okay, and then of course some outreach announcements and so forth. So great year for new members of the Ottawa Centre. 53 so far. Lori, Bill, Doug, Cheryl, Annie, Eric, Mike, and Jamie, and the Sims family. If any one of you are here, welcome. It's great to have you. So thanks very much. So members of the news, we always like to start off just with a couple. Let me start off with a couple of announcements. So this is for those of you who have the 2015 RASC calendar, if you flipped it to the November page, you'll have noticed this here. This is a submission by Peter Saragola, a member of ours that moved with Deborah, his wife, to the Okanagan, and this looks like it's a photo that they took of actually out there, and you can see there's a moon with Earthshine. I understand it's 28 days old, and Mercury off to the right here. A skill testing question for people. Anyone recognize what this is? All right, okay, so somebody was either reading my mind or was aware of my joke in advance. Yeah, it's a calendar. That's right. I was actually hoping that somebody would say, "Well, it's Venus." It's not quite. It's the where you hang the calendar from if you got a hook. So something I wanted to say that I think it's really important is that you're going to see, as I said later on tonight, you're going to see some outstanding astro images, and I think it's really apparent that the Ottawa Centre isn't a representative of the annual RASC calendar. You'll notice that some of them were for sale and are for sale tonight. When you walked in at break time, they're going to be available on the stage here. But I think more of our Ottawa Centre members should have their images published in that calendar, because we certainly got the talent here. And I think you'll agree with that. Okay, so Chris here, amazing. Okay, so that is, why am I going Ken Black? Ian Black, thank you. That was, so recently, Rolf Meyer was sharing some obviously Northern Lights pictures that he, actually this was a video that he shared recently and made his way onto the CBC TV weather broadcast. So nice going, Rolf. Ottawa Center member Rolf Meyer. Okay, so Gary's going to say a few things about the nomination process. Gary? Okay, over to you, Gary.
Thank you, Mike. First of all, could I just have a show of hands, our first-time visitors? Wow. Now, can I have a show of hands, our members? These are the ambassadors of our center. If you have any questions on astronomy, please ask these people. Don't stalk them, don't follow them home. But if you have any questions, Ivan's here, obviously, and a lot of us, feel free. It's Astronomy 101. So being past president, my job is to be head of the nominating committee for the next slate for 2016 of president, vice president, and so. And as Mike has mentioned, we do have rules that we have to abide to, and this is one such of the bylaws. Next month will be our elections, but we must have the notice 30 days in advance. So can I, next slide, please? So for president, we have Gordon Webster, vice president, and directors, you can see, Tim Cole, secretary, Chris Tarrant, treasurer, Oscar Echeverry, then councillors that attend council meetings too, Yves Demers, Carmen Rush, and Stephen Norris. Meeting chair is still open. I'm sure Mike is going to speak to each and every one of you in person because it is Mike's last night. Just as these people, there's a 2-year stint that the meeting chair has. So hopefully someone will come forward. It's a great position. I've had it for 5 years. You meet a lot of great people, and you really are in depth with the meetings. Then National Council reps, we have Brian McCullough and Robert Dick. And you can see there in yellow, these are 2 new reps because we must thank Rick Wagner and Bill Wagstaff for their fine contribution in the last 2 years going to national council meetings that represent the Ottawa Centre, either on the phone or in person, and many hours has been spent. So a round of applause for their great work. And last but not least, myself, being president, past president again for 2 years. Gordon will, if he wants, will become our past president. As you can see, a lot of all these are acclaimed, except for the new 2 people. They're incumbents. Next slide, please. But people, now this is not the end of the course. Any members that want to apply, they must submit for any position as you've seen. Nominees must be a member in good standing, meaning that you are fully paid up for the year, paid your dues. National Council reps must be at least 21 years of age, not for the other positions. And nominations must be sent to Chris Tarrant, our secretary, by 8 p.m. Eastern Daylight Time on November 29th, which is 5 full days before the December 4th meeting. So feel free to, again, have an input in the center. It's very, very rewarding. Next slide, please. And the appointed positions, you have Estelle, Chuck, Karen, Ron St. Martin, Jim, myself, 2 more positions. And in our Fraser hospitality, they have the tea, coffee, and sweets they've been doing for the last 50 years probably. They do a fantastic job. I hope they never leave. Al Scott runs the Loan Library, those telescopes. One great thing about being a member of the Ottawa Centre is you can rent a small telescope for $10 a month and binoculars for $2 a month. So you really don't have to buy that $8,000 scope yet. And Al Scott is Al Fraser's memberships. Next slide. I think that's it. Also, we're going to have the Paul Commission Observer of the Year Award. Please submit your observations by November 13th. There's a plaque that's handed out at our annual dinner next week. Anything else? No, that's going to be it. So again, this is the slate. It's not etched in stone yet. You have a month to put your name in, and hope you do. It's very rewarding. Thanks for your time, and enjoy this evening with Ivan. Take care.
Thanks, Gary. Actually, it's also worth mentioning a thank you to Eric and Eunice Gajula, who record this meeting and eventually makes its way onto YouTube. And it's also streamed live onto the internet for those of you who aren't aware of that. And so many of these people, they never seek gratitude. They just tirelessly come in and meeting after meeting, they do what they do, and then they come again, and they do it very well. True altruistic volunteers, that's for sure. All right, so our next speaker is Ivan Semeniuk, and Ivan, as I think you read in the agenda, he's going to share his latest, the findings on the latest research into dark matter. I'd like to say a few things about Ivan, just to give you a bit of background. So Ivan currently reports on science and science policy for the Globe and Mail. He's a contributing editor for Sky News magazine, where he focuses mainly on Canadian astronomical research. He's been reporting on science, and especially space science, for over 20 years, and has covered a number of landmark astronomical events, from the discovery of the first exoplanets to dark energy, to the Mars rover landings, and as recently as this summer's Pluto flyby. His reporting has taken him from the high Arctic, where he actually met Brian McCullough's daughter. It's another story if you're interested. To the VLT in Chile. It was a chance event, but an interesting one. He was also the writer and host of Cosmic Vista. That's the award-winning astronomy television series that ran on Oasis Channel. It's now called Love Nature. He's the former U.S. news editor for the journal Nature and was Boston bureau chief for New Scientist magazine. Before that, he spent 10 seasons as a columnist and field producer with Daily Planet on the Discovery Channel. Okay, going further back, prior to his years in journalism, he worked at the Ontario Science Centre, where he developed exhibits and programs and ran the planetarium there for many years. Now, he's a longtime member of the RASC. He told me he joined the Windsor Centre way back, I shouldn't say way back, when he was 14 years old, and then later I'm in trouble. And then later the Toronto Centre, where he became a lifetime member. He was the second VP at the Toronto Centre, where he organized guest speakers for the centre. So see, there's still hope for me. Finally, he has an undergraduate degree both in physics and astronomy from U of T, and a graduate degree in science journalism from Boston University. Now, he's spoken here before at the Ottawa Centre, we think more than once, at least 10 to 15 years ago. So if somebody can help me out and remember exactly when, that'd be good. It's a pleasure to have him back. So everyone, please give a warm Ottawa Spring Day welcome to Ivan Semeniuk.
Thank you very much for that introduction. It's very complete. I feel like you guys were orbiting a black hole for 2 minutes, and in that time, like 40 years of my life went by because of time dilation. So anyway, so now you've got the whole story. It's really a pleasure to be here and speaking to the Ottawa Centre again. I really actually can't remember when I last spoke to the Centre, but clearly it was more than 10 years ago. And it's been a few times, because I remember meeting Erin McCullough as a little girl. Because I think I actually stayed at Brian McCullough's house the first time I came to speak to the Ottawa Centre so many years ago. So the Ottawa Centre probably paid for that, for me to have that meeting with Erin McCullough. It's good you didn't have to pay for it the second time I met her up in Eureka. But that was a really, really fun coincidence, because she said, "Oh, I've met you before. You played my piano and you stayed at my house." It's like, what? Talking to this climate researcher, this laser physicist. Anyway, so I am a journalist. I'm here to talk about astronomy, which I love, but I am a journalist, and I work for the Globe and Mail. So I have to say, if there are any federal scientists in the audience tonight, come and speak to me afterwards, and we'll see what that feels like. That's great. I'm going to really resist. I know we're being streamed. I'm going to resist telling you all the stories. But let me tell you, it's not just environment and so on. Like, even trying to talk to astronomers who happen to work for the Canadian government has been unbelievably difficult at times. So I'm really looking forward to many more conversations that are easier and richer and happier for everyone. So on to dark matter, which happens to be the the topic I want to approach tonight. I'm approaching it as a journalist because I cover many different areas of news. And the way science unfolds, it's incremental at times. Many different groups are involved doing many things simultaneously. And there's a kind of gradual emergence of a particular story as people are kind of groping forward for understanding. And there are lots of different areas that are like this that are happening simultaneously. So, the world of the science journalist, you're kind of itinerant, you're kind of dropping in on people who are spending their entire research lives around a particular question, around a particular topic. And as a science journalist, you just get to parachute in for a few days, find out what they're doing, then, you kind of go off onto some totally separate topic. You might go from climate change to cancer to cosmology to whatever, and then come back again, a few years later. How's that experiment going? So, but it's nice when you step back and kind of put the picture together. And there certainly is, as I'm sure you're aware, there has been a very interesting emerging picture with the quest for dark matter. It's surely one of the most exciting and fascinating quests in the physical sciences in our generation, and there's a good chance that we are going to see some culmination to this quest. So that's why it's worth talking about, and I feel like really what I'm doing here is to kind of lay out a roadmap. I'm sure you all read about dark matter, you've all seen probably documentaries and so on, maybe see magazine articles, but here's just another chance to kind of put the whole story together to better arm you for news that might be coming in the next few years. So I'll try not to press the eject button and see if this works. And of course, this is a roadmap, and the first thing I'm going to do is take you on a detour because because I deal with news. I'm always compelled to try to put some news up front. So I'm going to talk about something completely different from dark matter in a minute, because this month is a huge anniversary, which you may have already been hearing about, but it's the 100th anniversary of what this fellow did, Albert Einstein. Here he is. At this point, his hair is not so white and not so frizzy. This is what he looked like in his study in Berlin. This is probably a little bit after 1915, but Einstein's crowning achievement was his general theory of relativity, a way of reimagining Newtonian gravity in a completely different way. And it happened. I mean, it took a long time, but it reached its kind of climax 100 years ago over a series of 4 Thursdays. These were Thursday lectures to the Prussian Academy of Sciences, where over 4 Thursdays he kind of presented his theory and was still working on it as he was doing these presentations, and kind of came to the final punchline on the 4th Thursday. I think it was November 25th, but it was right at the very end of the month. And this was the end of it. Like, there was a system of equations that are still used today, and basically, the bottom line is, instead of having Newtonian gravity, where you have this force that's acting from a distance, or somehow there's like the sun is exerting a force on the earth, or the earth is exerting a force on us that's pulling us down. And we're used to the mathematics of these forces. We learn about them in high school and so on. It replaced all of that with a completely different idea. There's no more force. There's nothing acting at a distance. Instead, gravity is entirely described in a new way that's geometrical, that has to do with the fact that space can be curved into a dimension that we can't see, and that it's the interaction between mass and the curvature of space that is producing this effect that we call gravity. And this equation, or this actually represents a set of equations. The left-hand side is what's called the Einstein tensor. So it's like a system of equations on one side. The right-hand side is called the energy momentum tensor. So it's the left-hand side of this equation that's kind of describing how space might be curved, and it's the right-hand side that's describing how things move. So basically, in the words of John Wheeler, who really helped kind of explain relativity to a broader audience in the 1960s, matter tells space how to curve, space tells matter how to move. It's a profound idea. It's still with us 100 years later, and it has an incredible corollary. So here's the picture. It's, instead of the equation, it's actually easier to picture it. You have that idea of a mass in some kind of an abstract fabric of space, and the presence of the mass is warping the space. And so something that normally would travel in a straight line now is following the curvature of space. It actually thinks it's still moving in a straight line, but it's now following that curve, just like a race car goes around a banked track. So that's basically what Einstein gave us. And there's a fascinating corollary to this that I wanted to draw your attention to this, because the 100th anniversary of this is coming up too. And this is going to lead to, I'm going to lead you to a Canadian news story here. But just weeks after Einstein presented general relativity for the first time, one of the first people to take it up and work with it was this fellow, Carl Schwarzschild. Now, he's already older than Einstein at this point. Einstein is in his mid to late 30s. I think he was 36 when general relativity came out. You know, Schwarzschild's already 42. He's the director, he's an astronomer, he's the director of the Potsdam Observatory. He's got 3 children, you know, and he's got, his scientific career. But he's also a soldier in the German army in World War I. He's also Jewish, by the way, and he volunteered for this. So this is like a mentality that would be hard for us to wrap our minds around now, 100 years later. But this Jewish father of 3 who was the director of an observatory just up and volunteered to be in the German army and be in the trenches in World War I. And what he was doing at that time was using his mathematics to calculate the trajectory of artillery shells, these long-range artillery shells, on the Russian front. But in his spare time at night, as a distraction from the battlefield, he was working with Einstein's equations. He was playing around with the motion of bodies in space-time. And Einstein was able to come up with an approximate solution to one of the burning problems in gravity, which was this weird behavior of Mercury. The precession of Mercury's orbit didn't appear to, it didn't move the way the way Newtonian gravity would predict. So Einstein had an approximate solution that showed relativity did a better job of explaining this. Schwarzschild actually reformulated Einstein's equations in an easier way that made the mathematics easier to work with, and came up with the very first exact solution to Einstein's equations that exactly predicted the movement of Mercury. So it was a big achievement, and he wrote to Einstein right away. Einstein was thrilled. He got the letter December, early January of 1916, and by January 13th, 1916, Einstein was presenting Schwarzschild's manuscript and saying, look, here it is. We've nailed Mercury completely. And it was it was like the first major feather in the cap for general relativity. And within 4 months of that, Schwarzschild was dead. He had contracted an autoimmune disease in the trenches, and hit that tremendous achievement was really his last great piece of science. So that was a huge loss. But the legacy lived on, because one of the weird outcomes of Schwarzschild's approach to relativity, and what became obvious in the mathematics, was that it allowed this, you see this green line here. So you see these these are the curve, these are kind of trajectories around a point mass, in space using relativity. And you can see there's this green line, and what that represents is there's this place around which, even something moving at the speed of light would not be able to escape space so severely curved. So basically, Schwarzschild's equations make clear that something like a black hole can exist. There had been previous ideas about something like a black hole, because, people had an idea that if light is moving at a certain speed, maybe gravity could overpower it. But they were very limited and kind of off base, because they neither had a proper theory of light nor a proper theory of gravity. Whereas what Schwarzschild had hit upon was the first, closing in on the first real description of what would come to be called a black hole. And that was almost 100 years ago. No one believed it at the time, but now we do. And not only do we know that black holes are real, but they can be detected, and they may actually be essential even to our own existence in the universe. And now we have, this abstract idea has gone from kind of a theoretical curiosity to something that's much more like a practical certainty. And we can even imagine what it would be like to have a black hole moving through space and to have a black hole devour a passing star, for example. Let me see if I can get this to work. Oh, great. Isn't that great? So that's how far we've come in 100. That's how far. Oh, there we go. We've got a little commercial for NASA there. That's how far we've come in 100 years. So that's a lovely animation because it's dramatic, but it also is scientifically, it has a lot of interesting scientific detail in there. It shows how, you know, a star essentially gets, it kind of disintegrates, is pulled out, the matter in the star is pulled out to form this accretion disk, you know, which circles around the black hole. And of course, you saw the black hole at first just by the way it's bending the starlight behind it, but that, you know, so light is bent by gravity. But then you're seeing how the matter is swirling around. You might have noticed that kind of pulsing in the disk, so there are different physical effects like that that have been predicted. And then these long jets coming out because some of the angular momentum is being released with these with this material that's flowing outward. It hasn't quite entered the black hole. It's barely escaped entering the black hole, and it's being injected at very high speeds. And in fact, there are pulses and stutters that are predicted in that process, and brightenings and so on. And there's, you know, the way black holes were originally detected, and it actually involved an observation made at the David Dunlop Observatory north of Toronto. First, there were these Xray sources in the sky that were found by the first Xray satellites. And the way the first black hole was nailed was that one of those Xray sources, Cygnus X1, was connected to a hot blue supergiant star that was orbiting something else, something that was not giving off light or not enough light to be seen by the 74-inch in Toronto, but it was, but clearly the blue star was orbiting around it. And it had to be so massive that the only explanation was it was a black hole. And that was sort of the first confirmation. So why am I telling you all this? Because in 2016, you know, early in the new year at this point, right about the 100th anniversary of you know, Schwarzschild coming up with this approach to relativity that essentially predicts black holes, we have a Japanese satellite, an X-ray satellite, that is going to do the most high precision measurements of X-rays coming from black holes out there in the galaxy to better understand the actual mechanism that's producing those X-rays and test some of the dynamics of what happens to matter that's immediately adjacent in this environment around the black hole. There are a lot of things that are not well understood about what actually happens in this complex environment where general relativity plays a very important role in what's happening and where gravity is kind of interacting with the whole system. So I'm telling you this because this Japanese satellite, you know, the way you measure, imagine this, I mean, you know what it's like, some of you have probably built telescopes. And you know, the basic idea, especially if it's a reflecting telescope, is you have a mirror and light comes in, the mirror has a bit of a curve, and light bounces off the mirror, and the curve in the mirror helps focus the rays. And so you can actually get an image, a magnified image, with a curved mirror. That's how a telescope works. What about an X-ray telescope? X-rays are much, much more powerful. If you tried to bounce them with a mirror, they would just go right through. I mean, this is what X-rays do. That's why we go to the dentist and have X-rays go through us. They'd go right through a mirror. So the only way to focus X-rays is to have something like a plate of metal where an X-ray can come in just at a glancing angle. And it can be, and if it comes in at a shallow enough angle, it could bounce a little bit. And so you can redirect that slightly. So then imagine instead of a plate of metal, you have a ring of metal that's tapered a little bit. It's almost like a part of a cone. and you could have X-rays coming in slightly redirected, slightly focused, and if you have a series of nested cones like this, you can actually focus quite a lot of X-rays and concentrate them and essentially create an X-ray picture from some distant part of the universe. The catch is, the more powerful the X-rays, the shallower that grazing angle is, because the harder it is to redirect those things. So you need a long focal length. You've got to have the cones or the cylinders over here and the detector way, way over there. For really high energy X-rays, which are the ones that astronomers want to get to study what's happening right in close to the black hole, you need a 12-meter focal length. That's a big, long thing. It's basically as long as this room. And and of course, you have to put it in space because these X-rays are not penetrating the atmosphere. So it's a big challenge for space astronomy. You need a 12-meter focal length, and somehow you have to launch that thing into orbit. So one way of doing it, an economic way of doing it, is to have a telescope that's all folded up, and it expands once it's in space. And then you have that long focal length. And that's what this Japanese satellite, Astro H, is going to do. But then there's a catch here, because if you're going to have, the reflecting surface is way over here, and the detector way over here, and you're working with such short wavelengths, like X-ray radiation, those two ends of the telescope have to know exactly where they are in relation to each other in order for you to get a coherent image out the other end. They have to know exactly where they are. So that takes a fancy laser measuring system, an alignment system, so that you have, because just think of all the vibrations and thermal changes, and this thing is orbiting around Earth, and it's getting sunlight and darkness, and you've got to have a really careful measuring system to keep these things aligned. Where do you go for something like that? Ottawa. Ottawa. NetTech in Ottawa built the alignment system for this satellite right here in your town, and that thing is going up maybe in January, maybe February, sometime early in the new year, on that Japanese satellite. So that piece of hardware built here is going up there. It's going to keep that telescope aligned, and it's going to allow us to see black holes better than we've ever before seen them, and kind of explore the world that Carl Schwarzschild opened up for us 100 years ago. So there's a news story that's hometown news for you, right here, hot off the presses. So that's why I took that detour, because I couldn't come to Ottawa and not tell you how excited and I'm looking forward to reporting on this mission. Let's keep our fingers crossed. Once it's launched, they'll rename it something else. Astro H is kind of a boring name for a satellite, but that's because they don't want to give it a name until it's actually okay and in space. I don't think they want to waste a name on something that isn't going to work. So, all right. So now let's move back to dark matter. Oh, sorry, and here's the actual system. I had one more slide for you. There it is right there. So that little silver box is what's going to make it all possible. From Ottawa. Anyone here from NetTech? Just wondering. Okay, well, shout out to you wherever you are. What is dark matter? Before we even talk about the 3 roads to dark matter, I think it's worth saying for a moment, what the heck is this that we're talking about? Why do we want a road to it? And why is everyone concerned with this thing? To do that, I just want to stop and show you one of my favorite pictures of the universe. This is a simulation. It's actually not a photograph, but it's supposed to be very accurate. It's a look into a spiral galaxy, looking into the heart of a spiral galaxy, much like the Milky Way. A little bit later, we'll turn this into a moving image, which is fabulous. It's one of my favorite animations. But what you're seeing here is, you notice there are no spiral arms. Where's the galaxy? And this is a picture of a galaxy like ours without the matter. The matter has been taken away from this picture, and instead, what would be dark matter, what astronomers think is dark matter, is shown here illuminated. So this is our galaxy, what our galaxy might look like through dark matter glasses. So if you could go outside at night, look out at the Milky Way, stretching out overhead, or if you go a little bit further south so you can really see the center of the galaxy up high in the sky, put on your dark matter glasses, this is what the Milky Way should look like. What you're seeing here are concentrations of dark matter. The densest concentration is right at the heart of the galaxy, but there are these subhalos, these clumps of dark matter that are like almost like fluffy snowballs swarming around, moving around the center. They're all dynamically orbiting around the center, but locally they've kind of broken up into these little clusters. That's the best guess for how dark matter is distributed in our galaxy. But we don't see that, but we're inferring that that's what's actually there, these subhalos. So let's talk about how could this possibly be true. And this brings us back to one of the classic arguments in natural philosophy. This takes us right back to the very beginning of thinking about the universe in a rational way. This is one of my favorite images. It's a close-up of that beautiful fresco that you can still see at the Vatican, the School of Athens by Raphael. This is a close-up of the very center of that picture, where you have the two key philosophers of the ancient world. The older fellow who's pointing up is Plato. The younger fellow who's going straight ahead, no, this way, is Aristotle. And they're sort of depicted here kind of in philosophical debate. And they do sort of represent two different ways of looking at the universe. And I think it's instructive to help think about why dark matter is so important as a question, important to science itself. Because Plato kind of embodies this idea. If you remember Plato, there's the thing about the cave and that we're just, our perceptions of reality are just like looking at shadows on the cave. And if you could actually step outside the cave, you'd see the things that are casting the shadows. You'd see things the way they really are. Plato is kind of telling us there's more here than meets the eye, that our perception of reality is limited. Aristotle, different. Aristotle's the empiricist, the guy going like this. He's like, no. What you see is what you get. What you can measure is knowledge. That's it. And don't make stuff up. If you don't have to, don't make stuff up. That's not the way to go. And these philosophical debates still thread their way all through the history of Western thought right to today. And you still see them coming up in different ways. You see them coming up now when people are talking about things like other universes or what the deal is with dark energy and so on. There are questions about the limits of science, or do we need to make up this whole other structure to reality, or is that too much? And it's an active debate. So dark matter is kind of that debate. And most of science is case two. So a lot of the discoveries that are made in science are made through that Aristotelian way of looking at things. Not by making stuff up, but by sort of applying what is known and taking that as far as it can go to create new insights about what's out there. And that's a lot of science today. On the other hand, every now and then it's the other case, where you have to devise something entirely new, something unexpected, something that was really not wanted in a sense, because it makes everything really messy, an entirely new effect or an entirely new law of nature in order to explain it. And what happens is when that happens, then things get really exciting, because it kind of breaks the paradigm and you have to reconsider how science works. So here's a case for rule 2. When we see these effects in astronomy, here's the situation. The planet Uranus was moving in a way that was not as predicted by Newtonian gravity. Scientists used this to predict that there must be another planet. So this is case 2. They're not saying, oh, the universe is behaving in a way that we didn't expect. They're saying, actually, the universe is behaving exactly as you should expect it to if there's another planet that we didn't know was there. And in fact, this is Urbain Le Verrier at the Paris Observatory. This is an image of him that was created for a proposed mural of great French astronomers or great Paris Observatory members. And, he's sort of shown pointing off, and he's got his pen. He's the one who discovered a planet with the point of his pen. That's how it was stated. he's doing his mathematical calculations, and he's showing, my calculations are telling me that if you look for a new planet, you will find it there. And that's exactly what happened, and that's how Neptune was discovered. So that's case 2. It's exciting, but it is an extension of our knowledge, our known laws of nature. Here's a different case, the one I mentioned just a minute ago, Einstein and Mercury. When Mercury was found to be orbiting in a way that was not as predicted by Newton, one approach was, well, maybe there's some planet inside the orbit of Mercury that's actually throwing off its orbit. Maybe there's another body in there. That didn't quite work, and in fact, searches for that object came up empty. And instead, the answer was case 2. It took Einstein to say, no, it's not that there's another planet that's throwing Mercury off of its orbit. It's that our understanding of gravity is incomplete and we need to completely change gravity. That's an earth-shattering approach. That was case 2. So the situation then is, when you have an effect that you don't understand, and dark matter emerged quietly, gradually, as an effect that increasingly became harder and harder to explain, there's this question mark hanging in the background, maybe unstated, but there's this implicit question mark. Is this case 1 or is this case 2? Are we going to find something that we understand but we just didn't know was there? Or are we going to have to completely change the laws of nature in order to account for this phenomenon? That's why it's an interesting problem and an interesting story to follow from a journalist's point of view. The story starts in 1930, not long after special relativity, not long after we understood that there were things beyond the Milky Way that were other galaxies. And of course, here's a picture of the Coma cluster. Many of you have probably seen this cluster of galaxies in the springtime sky. There's Fritz Zwicky, European astronomer who later came to work at Caltech. It was Zwicky who looked at the measurements of the speed of the galaxies orbiting each other in this cluster. And he made the realization that they are moving too fast for this picture to make sense dynamically. They should be flinging themselves apart. They're whipping around each other so fast. The only explanation is there's a lot more mass in this system than you would appear to have from if you count up the galaxies in the photo. There's more mass in there than meets the eye. And it was Zwicky who actually used the idea that there's some kind of dark matter, and we have to understand what this is. And there are all kinds of ideas you can imagine for what it would be, but that was the first hint that there's something out there that is beyond just the stars and galaxies that we can see on photographic plates. So this grew through the second half of the 20th century, and it was done most precisely and beautifully in the 1970s. Here's Vera Rubin, one of the key astronomers who was involved in these measurements. In this case, not looking at a distant cluster of galaxies, but much more precisely at the rotation of a nearby galaxy. Here's the Andromeda galaxy. There's Vera Rubin's making her very careful measurements, looking at how fast stars on the outskirts of the Andromeda galaxy were orbiting around the center of the galaxy, and finding that those stars were moving too quickly, that the orbits were not like not the way Kepler would have said they were. So for example, in our solar system, as you go further and further away from the sun, the planets get slower and slower. As Neptune takes, I can't remember how many years to get around. Pluto takes even longer. Like, it takes a long, long time for these outer planets to go all the way around the sun, because as you get further and further away, the force of gravity falls off in that way. It's the inverse square law. But that was not happening with these nearby galaxies. The stars in the Milky Way are orbiting almost with kind of a constant velocity as you go further and further out with radius. So the way to make sense of that is to imagine that there's a massive halo of material that is invisible in these astronomical images. Somehow it's not seen, so it's not blocking light, but it's also not giving off light. And it's slowing down the motion of these distant stars around the center. That was in the 70s. By the 90s, you had a very different kind of evidence. Here, you're using the Hubble Space Telescope to look at very distant concentrations of mass, even more distant clusters of galaxies. And what you're seeing are these arcs. You see these kind of arcs, are these circular, gosh, that's scary. These circular features around the kind of, the black hole. Anyway, they're centered around the center, the concentration of mass at the center of this cluster. And what's happening there is the gravity of the cluster is bending the light of the galaxies that are far off in the distance, just like a big spherical lens would bend the light and kind of distort the image. So those arcs that you see are more distant galaxies in the background and the light is being bent. But the amount that the light is being bent excuse me, allows you to calculate the mass. And again, you can find that there's much more mass there than there should be based on the galaxies. So these are all clues that are becoming more precise. I'm going to jump right now to just 10 years ago, where you sort of have the most, what's sometimes called the smoking gun for dark matter. And so I have to explain this picture a little bit. This is the bullet cluster, if you haven't seen it before. So this is two clusters of galaxies that have just collided with each other. And they've essentially passed through each other. So it's like, like two buckets of sand or something passing through each other. So you can actually see the two clusters. And I'm going to see if I can use the pointer here. Oh, this is great. So here's one cluster. You can really see it concentrated here. And here's another cluster right there. And they have just passed through each other. You can tell that because of, like using the Doppler shift and so you can sort of tell from their motion. But now here's the thing. This bluish stuff, this is not real light. This has been added to the picture artificially. What that's showing you is where the mass is most concentrated. And how they're getting that is, just like I showed you those arcs in the previous image, those are really extreme. Let's just go back for a moment. These long arcs you see here, this is a very extreme distortion. But there are also smaller distortions, just very weak distortions of background galaxies. And in these images, there are also very small distortions of background galaxies, and you can use that to figure out where is the mass most highly concentrated in the foreground. And the blue shows you, that's been artificially added to the picture to show you where, according to the weak lensing, the mass is most highly concentrated. But here, you have this pink stuff. The pink stuff is emission from X-rays. The Chandra X-ray telescope picked this up. This is hot gas, very, very high temperature, rarefied gas. The kind of gas that's between galaxies in galaxy clusters. What's happened is the galaxies have passed through each other, but it's not so easy for these clouds of gas to pass through each other. So they've collided, and there's a kind of friction there. You have two clouds of gas that are moving with the galaxy clusters, but they can't pass through each other that easily. There's drag. And so you're seeing that here. There's a lag time with the gas as it's passed through each other, and it's energized by this. So this shows you where the gas has been stripped away, where stuff that's made of atoms has lagged behind, and yet the highest concentration of mass has continued to move along. And there's not nearly enough, the galaxies themselves are not nearly enough mass. So there's a big amount of mass, oh thank you very much, a huge amount of mass, two huge amounts of mass that have just passed through each other without interacting. And yet the gas clearly has interacted. So it's something that's non-baryonic, something that's not like gas at all. And by the way, this picture also presents problems for alternative explanations to dark matter that are just sort of modifying the laws of gravity. It's people who would say that it doesn't totally rule it out, but it makes it a lot more complicated. And then we have this situation now. This is sort of contemporary, so the last couple of years. This is a view of the cosmic microwave background. It's the entire sky in microwaves mapped out by the Planck satellite. There were Canadian team members on this too. I'm just going to take some water. And those speckles in the cosmic microwave background reveal details about the amount of mass and how that mass is concentrated and the nature of the mass in the universe. So, there's a scaling effect here, in terms of where you tend to see the the different scales at which you tend to see clusterings of these speckles and spots. And when you do this mathematical analysis, it's not a totally random distribution. And what that tells you is, there's a certain amount of mass that's actually quite small that interacts with itself. This is matter. There's another amount of mass that behaves differently, but its presence is there. It's written in the signature of this image. That's the dark matter. And then there are other factors as well that contribute to the total mass energy density of the universe. And this is basically what they've come up with. These are the most precise measurements based on the Planck data. You have baryonic matter, which is basically atoms. That's us, planets, stars, galaxies. That's just under 5% of the mass energy budget of the universe. Then there's this other share, which is the dark matter. Unknown matter, but it's in some kind of form of matter that's not atoms. And so it's not asteroids, it's not gas, it's not whatever, it's something else. And then there's this dark energy, which is this amount of energy that's present in the vacuum of space that continues to be present and is not diluted as the universe expands. So it'll be an ever-increasing share. But that's the share of dark energy from that view of the universe. So basically, even if you had no other evidence, and you only had the cosmic microwave background, astronomers would already be inferring that there must be something called dark matter out there, even if we had no other clues. But of course, we had all these other clues ahead of that. So that consensus would tell you that dark matter is cold, it's non-baryonic. Cold means it's not moving around very fast, and non-baryonic means it's not atoms, it's something else. That makes it case one. That makes, like, we have to imagine something entirely new laws of nature. We have to add new particles, or we have to create new laws of physics in order for this stuff to exist. That's why it's so exciting. It's something out of the standard description of nature as we understand it today. But the question is, what is it? And what is this new description, and where is it going to take us? And why has not a Nobel Prize been awarded for this? Because after all, dark energy, which I referred to just a minute ago, it was discovered in 1998. And that was one of the other exciting things I've had a privilege of covering as a journalist, being in the room when that was first announced. And, those Nobel Prizes have already been handed out. So it's funny, dark matter is a very different story. It emerged much more gradually, under a lot of skepticism, until eventually it's sort of become, the most likely scenario. But it hasn't yet been detected, and no Nobel has been awarded yet, although I would say Vera Rubin is certainly deserving of a Nobel. So I show this slide with all of these different doors, and I want to just refer for a moment to the fact that there are alternative explanations. So imagine, when you're presented with a new phenomena, what door do I go through? How do I characterize the different possible explanations? So, one door could lead to proposing a new kind of matter, a new particle or a new family of particles that we didn't know before, but they must be there. And then there are many different theories that could explain many different types of particles and why they would exist. That's one whole branch. The other branch would be, no, instead of inventing new particles, let's do what Einstein did, let's change the laws of gravity. Maybe what's happening is, it seems like it's matter, but maybe it's just that at larger and larger scales, gravity behaves less and less like Einstein predicted. This is less popular at the moment for a few reasons. First of all, general relativity has withstood so far every measurement, every test that we've been able to give it so far at every scale, including binary pulsars and other things, or putting clocks up in orbit. And in fact, general relativity is so well understood at this point that GPS, like the GPS system in your car or your phone, would not work without general relativity. There's actually correction built in just because there's time dilation. The satellites that are orbiting, I think they're 20,000 kilometers above the Earth's surface. They're not quite geostationary, but they're up there. They are feeling gravity less strongly than we are on the surface. And as a consequence of this, time for us is moving more slowly than for those satellites, as Einstein would have predicted. And so that has to be corrected for in GPS systems. And if it wasn't corrected for, within, I think within 30 seconds to 2 minutes, your GPS would be like 10 kilometers off in telling you where you are. So like it's that much a part of our practical everyday life, Einstein's relativity. So that's how much we depend on it. We've never found that theory to be inaccurate at the moment, so far. It's so far withstood every test. The other problem for these other alternate theories of dark matter that would replace the dark matter with just a different kind of gravity is that things like the bullet cluster are really hard to explain with that approach. And you end up with a situation where you can modify gravity mathematically to a certain extent, but then you still have to add a little bit of dark matter anyway, just to make everything work. And so then it's like, well, if you have to have the dark matter anyway, maybe that's the whole story. So that's where it stands with this. So on the other hand, if there are other particles, then we should be able to find them or create them or somehow detect them. And that's the key question. So here's one idea. This is the idea that's sort of been dominant for the last little while, but its dominance may be about to end. This is the supersymmetry idea, that for all, on the left-hand side, you see all the particles that make up matter in the standard model. This is everything we have understood, and at this point, these have all now been discovered. So, there's matter, which is, 6 quarks and 6 leptons. The quarks, of course, the two that we are most familiar with are the up and the down quark. They make up protons and neutrons. And then there's the electron, the best known lepton, and the neutrino, the electron neutrino. But there are these other quarks and these other leptons as well. And then there are these charge carriers, the photon, which carries light, the gluon, and these Z and W bosons, which mediate the weak force. And then on top of all of that, there's the Higgs particle, which comes out of the Higgs field, and you need that to explain why some of these particles have mass and some of them do not. These guys all have mass. Photon doesn't. So how does that work? It's because of the Higgs, and now the Higgs has been discovered. So these have all been verified by experiment. But the idea is perhaps there's a whole other family. So here basically you have one group of particles that have a certain kind of behavior here, and another set that have a different behavior here. So the idea is that maybe there's a symmetry where you have another set of particles where that property is reversed, and that would be this whole supersymmetric family. So there'd be a whole family, and they have different names. Instead of quarks, there are squarks. Instead of leptons, there are sleptons. And instead of a Higgs, there's a Higgsino, and so on. And perhaps the lowest mass particle of all, and these particles maybe would decay the way some of these higher mass particles decay, but they would have to decay into a stable particle. And in some models, it's the neutralino that is the most stable particle. So maybe the universe is full of neutralinos, and that's what the dark matter is. So that's one idea, and that's one family of explanations that are called WIMPs, weakly interacting massive particles. So they interact a little bit with matter, not a lot, and they would be very massive particles. So a lot of how galaxies and galaxy clusters behave and how light behaves and how space is warped when we look out into the universe would be explained very well if dark matter was this kind of particle. So now we go on the 3 roads in search of these particles, and I'm going to take you on 2 very quickly and spend a little bit more time on the 3rd. So if you're going to be on a road, you need a road map. So here's what our road map is going to look like. And get familiar with this map because we're going to see a lot of it. What you're looking at here is a Feynman diagram that kind of describes particle interactions. And this would be if you have a weakly interacting massive particle, so a particle that could occasionally interact with regular matter, you could have some sort of reaction like this. So this Greek letter here, or chi, and this one here, these represent 2 dark matter particles. And they're on a trajectory that brings them close enough together so that they interact. And because there's a chance of interacting with ordinary matter, whenever you have that sort of situation, there's a slight chance that ordinary matter could be the end product of the reaction. So you could have 2 particles of dark matter hit each other, and have 2 particles of ordinary matter come out the other end. But because these things are very massive, and they have to be to account for all of that mass that dark matter, we know dark matter is giving us, that in return, these guys would be coming out with very high energy, because they're lower mass. So you have to look for a source of really high energy, ordinary matter, which might give you a clue to dark matter annihilation. There's an experiment right now that's doing this. This thing, AMS, this particle experiment that was brought up to the space station on one of the very last flights of the space shuttle. I think it was the second last flight. Installed up there, it's basically a giant magnet that's drawing in particles moving through space. This is a cross-section of what AMS looks like. Charged particles that are flying around the galaxy come in, and depending on their charge, they're bent one way or another way by this donut-shaped magnet, and they're very precise detectors that are measuring the energy of these particles. And what we're looking for, what scientists are looking for, is a signal that would indicate that there would be, an excess of particles at a certain energy. A lot of them would be expected anyway, because we know the galaxy is full of cosmic rays, and there are lots of ordinary processes that produce these massive particles, these high-speed particles, high-speed protons, high-speed electrons, and so on. Cosmic rays, supernovas, lots of things that are out there. But if you remember that picture of what our galaxy looks like when you put on dark matter glasses, so it could be that at the center of our galaxy, where the dark matter is most concentrated, there are a lot of these dark matter collisions going on, and maybe an excess of high-energy regular matter particles coming out of there. And those would be detected by AMS. So here's what the data looks like. This is the positron data. So these are, like electrons, but they're positrons, positively charged. And what you're seeing here is, it would be at the very high energy level that, if there was no dark matter annihilation, it should be following this curve. Now, what you're seeing here is, it could be diverging, but you notice that as you get higher and higher energies, the error bars on the data are growing. And at the moment, the error bars are so wide that they're consistent both with dark matter annihilation or no dark matter. So it's not precise enough yet. And the reason is because as you get to higher and higher energies, the particles have become rarer and rarer. So you have to wait longer to build up enough data to actually get a precise measurement. And so that's where we stand right now with AMS. They're trying to build up their data. But there's another wrinkle here, which is there are a lot of other possible explanations for high-energy protons, for positrons, which could include black holes, those jets. There could be other ways that positrons are being accelerated. So AMS can also measure protons and antiprotons. Those are even more rare. But the idea is that in another few years, when the proton data comes from AMS, provided AMS can keep running, and there is a question mark over how long it can last, we may finally get an answer. So it's really the proton data that will be the next big step in this experiment. But so far, it's allowing for the possibility that there are some dark matter annihilations, but it is not, the final word. Now, the funny thing about roadmaps, if you've ever, not quite sure where you are, if you ever done the thing, I should be looking at the map this way. Well, these Feynman diagrams are exactly like that. You can imagine a reaction one way, but you can flip the map around and do the same thing the other way. So just like you could have, kind of two dark matter particles colliding to create ordinary matter, you can reverse the map and imagine the reverse scenario. Imagine two very, very high energy particles, ordinary matter particles, coming together. Instead of waiting to have high energy protons coming to us from the center of the galaxy, what if you had two high energy protons deliberately crash into each other and have enough energy that maybe what would come out the other end would be two dark matter particles? So where can you have two very high energy ordinary particles collide into each other? At the Large Hadron Collider. This is what happens at the LHC. This is a picture way back in 2008, just before they sealed up the LHC for its first run. I was down there. I took this picture just to give you a sense of, it's a 27 kilometer long ring, and you see some of the magnets here that are guiding the beam. You have two opposing beams that cross at certain points. And when they do, here's the big giant ring. And there are only 4 points where they cross. And the two I want to direct your attention to are Atlas and CMS. And these are the two major experiments where they are looking for new physics from the energy of the collisions, these very high energy proton collisions. Atlas, by the way, is the one that our tax dollars are invested in. There's a fairly high Canadian contribution to Atlas. Here's CMS. This is a much younger version of myself at CMS. CMS is huge. It looks like this when you're down at the bottom. This is before they sort of put it all together. Here's Atlas. Again, at the very center of this is where the beam would come through. And what you're seeing all around it is this giant set of detectors. Here's a map of Atlas that kind of shows it. And some of these detectors are built in Canada. And so as the beam comes through, the idea is that when you have a collision, the byproducts of that collision will spray off in all directions. All of these particles and all of the detectors all around can detect all of those different particles that make up the byproducts of a collision. You add it all up together and you sort of have the energy of the total collision. And that's what it normally looks like. That's the kind of thing that led them to the discovery of the Higgs boson, which was announced in 2012. You get a telltale pattern of collisional byproducts. You do that enough times, you get however many billion collisions until you're sure of what you're seeing, and then you can say, we have discovered a new particle. There's no other explanation for this. Dark matter would be a different situation. Instead of the shower of particles, you'd sort of have maybe only particles going in one direction and nothing going in the other direction. It would be like something is missing, because if dark matter were created in these collisions, that dark matter would then drift off through the detector and not be noticed. The detector would not pick it up. So you would be looking for missing energy. That would be the signature of dark matter in the Large Hadron Collider experiment. They didn't find anything like that in the first run. Now, since May, the Large Hadron Collider has been going at double the energy, almost 13 TeV collisions. It's remarkable how high the energy is. This is really the zone where it's possible for them to penetrate into where there might be new physics, and where some models predict there should be some of these supersymmetric particles. You notice, however, it's May, now it's November, 6 months have gone by, no one said a word. So dark matter has definitely not been pouring out of Atlas or CMS. That doesn't mean it's not there, but if it's happening, it's not happening very often, and it's going to take a long time to build up data, or it may not be happening at all. So there's a very uneasy silence right now coming from the Large Hadron Collider. This is the first collisions back in May. So now, let's take the third road. Once again, we're going to play with our map. Instead of turning it around 180 degrees this way, we're just going to turn it 90 degrees. So now, so let me do the 90-degree rotation. There we go. So instead of having two dark matter particles or two ordinary matter particles collide, let's have a dark matter particle interact with a regular matter particle, a standard model particle, and then two particles come out the other end. And what this is basically a scattering. This is like a little elastic collision. It's like the dark matter particle is coming this way, it bounces off the matter and keeps on going on its merry way, and the matter keeps on going its merry way, but that matter has now been energized just because it's been jostled by the dark matter. It's like a very heavy hockey player suddenly running into you, and now the dark matter, the matter knows that something has happened to it. Where do you do that? Down underground, deep underground, not far away, a few hours from here, down in the bottom of the Creighton mine, down near Sudbury, Ontario, where the Sudbury Neutrino Observatory was built, and where now we have Snow Lab, which is this deep particle lab facility. This is a photo down there. And I went down there, and I think to sort of simplify the experience of what it's like to go down there, I'm just going to show this video. So maybe if you click on this one.
For these scientists, the daily commute means going down, way down. That's what it takes to get to Snow Lab, an underground laboratory near Sudbury, Ontario, that's at the leading edge in the hunt for dark matter. their reward could be a spectacular scientific discovery. Despite the fact that dark matter makes up 85% of the stuff in the universe, scientists still don't know what it's made of. It was discovered decades ago because of its gravitational influence on things we can see, like stars and galaxies. But apart from that, dark matter is virtually undetectable. After traveling down more than 2 kilometers and walking about a kilometer distance through this working mine, we finally come to the main entrance of SNOLAB. On the other side, it's a different world. Instead of a dark and gritty mine, it's a brightly lit laboratory that's cleaner than a hospital operating room. This is where you'll find an ambitious experiment called Deep 3600, which is aiming to be the most sensitive dark matter detector ever built.
What you're seeing here is the heart of the experiment. When the experiment's running, there'll be over 3.5 tons of liquid argon inside this acrylic sphere. If a dark matter particle comes sailing through in just the right way, it might jiggle one of those argon atoms, causing it to give off light. Light that could be picked up by these detectors all around the sphere. And that's what the scientists here are really looking for.
Scientists hope to have the experiment up and running by the end of 2014. So far, detectors like this have mostly shown us what dark matter is not, which helps to narrow the search for the next generation of detectors. But if researchers at SNOLAB are really lucky, they may strike dark gold and finally solve one of the deepest mysteries in the cosmos.
So, that introduces you to one of the realities of science. I think I said there by the end of 2014. And I thought I was being generous, like giving them lots of slack. And it's now, of course, almost the end of 2015. Deep 3600 is still not yet taking data. But I just spoke today with the director of SNOLAB, who tells me that they are about to load up that liquid argon. So they think that as early as January, they may be starting to get some data from Deep 3600. There's also another dark matter experiment, MiniClean. In fact, I'll just go right to it. There's a ton of dark matter experiments literally down there. Lots of different approaches. There's Deep 3600 that I pointed out before. Here's MiniClean. There's PICO, which uses this is a kind of a small proof of concept approach. And here's DAMIC, which is another one. So there are a number of different approaches to searching for dark matter, but they all involve the same basic idea, which is that as dark matter passes through a medium, it could jiggle or jostle a nucleus of an atom, and that atom would then be stimulated to give off radiation of some kind, and that can be detected up and above the background. I mean, that's also going to be happening because of cosmic rays, and at a certain sensitivity, it's going to happen because of neutrinos. But there's enough room to explore, and if you see an excess of motion in these nuclei, maybe they're being bumped around by dark matter passing through. And the really exciting one, and I'm just showing you what the detectors look like. They have these really interesting germanium detectors. This is Super CDMS. This is a major dark matter experiment from the United States. This is something that is being funded by the Department of Energy. And instead of building the experiment in the US, they've decided the best place for the experiment is in Sudbury. So that is going to go in 2017. By 2020, they could be taking data. That's another major experiment. And what they're trying to do is press the sensitivity of these experiments deeper and deeper. So what you're seeing, this is a bit of a complicated plot, but you're seeing mass on the horizontal scale here, and here's sort of the likelihood of interaction, the cross-section, where how likely is it the two particles will interact with each other. So experiments so far have kind of ruled out this zone, and then if you go too far down, there's so many neutrinos causing an effect that you would not be able to measure it because you'd be swamped out by neutrinos. But in the meantime, in the intervening space, theories predict the possibility that you would find dark matter particles. The supersymmetric particles I mentioned could be somewhere in this space. There are other models that are not involving supersymmetry. These are asymmetric dark matter models. There are some over here. So there's room to explore. There's still possibilities that particles would be found. And in fact, even though everyone would say, look, we need to pursue in all different directions, it may well be that it's these direct detection experiments that are the ones that are really going to nail dark matter because they kind of have the broadest. I'm really sorry, everyone out there on the web. They're really going to have sort of the broadest amount of parameter space to explore. So that's what we have to look for over the next few years. And the interesting thing is, of course, that there are, that this is happening right here in Ontario. Now, that facility was created for one experiment in particular, to measure solar neutrinos. And as we know, this year, that experiment was recognized with a Nobel Prize. How great is that for Canada? A Nobel Prize because of a Canadian facility. So here's another opportunity for a Nobel Prize with some of these experiments that are now going into Sudbury. So, and who knows, we might be hearing more about awards for these facilities. It's really important for Canada to have these big science facilities because it includes us in the international search. So I was just going to finish by saying, don't forget, like all of this sounds very esoteric. Like you're building detectors for something that may not exist. You're crashing protons together looking for signals that disappear mysteriously, but they don't. You're looking for particles coming from the galaxy, but they could be coming from all over the place, and who knows? It all sounds right on the edge of like, is this even real? Like, why are we even bothering with this? It just seems so tentative, so tenuous. But the point is, don't forget that we know that there is something out there. The universe at large scales is behaving utterly unlike it should, according to the rules of gravity, according to our known standard model particles. Here's that beautiful view of the galaxy. This time I'm just going to finish off by, let's fly through the galaxy with dark matter glasses on. And if we can do that, it's just such a beautiful experience. Again, so imagine you're hopping in your spaceship, you've put on your dark matter glasses, the stars disappear, the spiral arms of the galaxy disappear, you're just seeing the dark matter now, and this, this clustering, these subhalos of dark matter that are formed and that could be passing through us right now and we wouldn't even know. This is what most of the universe is in terms of its mass content. This is the real universe as far as we understand it. Ordinary matter is like the snow that you see on the top of the mountain. The mountain is dark matter. Okay. And thank you, Tangerine Dream. And I was just going to say that what this kind of search and covering this kind of science reminds us of is that, when we look at other things in nature, strange phenomena, and we create these elaborate experiences, it's often discussed or described as exotic physics or exotic particles, kind of exotic forms of theories. But in fact, what this is really telling us is like we're the exotic things. Like what we're trying to discover is actually the real universe, what most of the universe is. We're the exotic things, like we're the ghosts, and we're trying to find, the stuff that makes up most of reality. But on the other hand, it's good to be a ghost because, with dark matter, if it doesn't interact with itself very much, if it doesn't clump together, the reason why dark matter forms those beautiful halos is because it can't lose energy through collision. When atoms collide, they give off light and they lose energy, which allows them to clump together. They can form molecules, they can form planets, they can form life. So that's why it's good to have life. My goodness, I'm going to just break up every dramatic moment in this talk. That's why it's good to have light, and so that's how I'll finish the talk. Thank you very much.
Thank you, Ivan. Maybe we'll just
I can say that we've had some fine speakers over the last 2 years here, but I think I can say without reservation, you have been by far the most impressive and far the most interesting. Would you agree with that?
That's very kind.
Okay, let's see if I can get this microphone to work here. Test. maybe I won't. We have some time for some questions here, but maybe I'll start off with just as I was writing down some questions, you went through and answered each one of them in advance. So
That's because there's never time for questions.
it sounds like we're months away from direct detection of dark matter. What do you think?
So are we months away from direct detection? Well, I have to say I have to kind of measure this with reality because, even in that video you saw, by... Oh! Now, that might have been a direct detection right there. Something just passed through. These experiments, as I was reminded today, are extremely complicated. They take years to conceive, years to build, and years to analyze in the sense of trying to zero out or account for every other possible signal. There are a lot of ways of jiggling atoms deep down. Now, the reason the experiment is down below ground is to screen out as many cosmic rays as possible, but there are still some cosmic rays. There's still radioactivity down there, and there's contamination. You can only push it down so far. So that's the thing. How well can you eliminate other possible explanations? And that's why you need more than one experiment, and that's why it's going to probably still have to run for a while. But that's why I say, in our lifetime, in our generation, I think there's a lot of real hope that we're going to see real results. And I think that's why there's been an escalation of investing in these experiments. But it's going to be a very interesting story to follow, and there could be results. Well, there could be news. At the moment, the news is non-detections and how much they're chopping off pieces of parameter space. We don't have to look here anymore. We've ruled this out. We've ruled this out. So, and that's a little bit how it was when they were finding the Higgs.
Okay, Chris, can you turn the lights on, please? And I'm assuming this mic is working now. So if you could raise your hand, and if you have a question, I'd like to hand make sure you have the microphone. Any questions, Jonathan?
Yeah, this is one beautiful quest that mankind is on here, beautifully explained by yourself here. And notice that your last quote here is from the book of Genesis in the Bible, which reminded me of a theory that I've recently heard, and I'd like to get your opinion on. These astrophysicists have what they've done, they've tried to examine this question by going back to the original Big Bang, going right back to the Big Bang and the huge amount of energy that existed there, and using relativistic quantum new physics, they have expanded the universe with that tremendous amount of energy flowing out through the universe, and calculated that the expansion, as it's going out to the Hubble deep field, as we're seeing there, the expansion would impart energy to the galaxies as it moved out to the edge of the universe. So when they calculate the amount of energy that is being imparted as galaxies are being formed through this initial expansion of super energy, that dark matter is not needed. That what we're seeing is residual energy left behind by the Big Bang. Now, and they have all kinds of equations. I'm not a scientist, but looking at it, I say this is a very novel explanation that does not require dark energy. Have you heard of this idea at all?
So I have to say two things. First of all, I have to laugh because when I first put the slideshow together and I had the Let There Be Light, instead of this picture of TMT, I actually had the William Blake creation. I love that print by William Blake, and I thought, oh, people are going to say I'm like referencing Genesis, so I'll put TMT there instead. But of course, you still caught me. So yes, I'm absolutely referencing the Bible here because I'm a journalist and I can quote whoever I want. It's eloquent, regardless. But having said that, there are certainly alternative explanations, and there should be, in addition to this quest, a vigorous effort to pursue other directions theoretically. I can't speak directly to the one that you're raising because I don't know that in detail. But I would say when you're talking about that energy imparting, the first instinct that jumps to my mind is, when you have things like the rotation of the Andromeda galaxy, we're not talking about high energies here. We're just talking about the normal rotation of stars in a galaxy. So I'm not sure how that would explain that. And I think we would have to go to the source to see how the theorists would say. Even among people who debate this, there are researchers who would, like the bullet cluster, immediately they said, they actually, the title of that paper was, I can't remember how they worded it. It was basically verification of dark matter. Like they put it in the title of the paper and basically presented it as this rules out those who would say there's no dark matter. And right away, the people who are in the camp of the modified dynamics would say, no, we can fill it with the theory, and there's another explanation. So it's an active debate. But I would say, by and large, the momentum and the funding and sort of the scientific center of mass is around the dark matter, partly because it's so consistent with so many other things, including kind of the cosmological model. So I think that's the other thing. Like it just fits with everything else, but yet to be verified.
I have a question in the front there.
Yeah.
I'll just talk. I can talk real loud. Einstein.
Yeah.
When you have Newtonian equations, they don't work at relativistic speeds.
It's okay now, John.
It's okay now? Okay. What I'm saying is, with Newtonian, when you get close to the speed of light, his equations don't work. Let's take it the other way. With Einstein's equations, if you go back to Newtonian speeds, will Einstein work at those speeds?
Yes. So you're actually talking about special relativity when you talk about approaching the speed of light. But yes, in special relativity, as
Can you go behind the microphone?
sorry.
And repeat the question.
In special relativity, as velocities get smaller and smaller, the equations come to resemble Newton's equations. Like it's basically like Newton is like the limiting case of Einstein. When you're at low velocities. So and that's true in other words. The bigger issue though is that special relativity is completely different from quantum mechanics. Like just in terms of how the math works and in terms of what it the phenomena that it describes. So a big preoccupation of theoretical physics today is how can you have these two very successful theories, quantum mechanics and relativity, and they're not kind of commensurate with each other in an obvious way. There are many different versions of quantum gravity and string theory as an approach to this, and different descriptions of gravity from a quantum perspective. And people are now beginning to look at holographic models and come to deeper, in some cases kind of making deeper inferences about maybe space and time are not what we think they are. Maybe they're emergent properties of deeper laws. That's where we're at right now, and nobody knows where it's going to end. So you have to have Lee Smolin here, among others, or people from the perimeter, and they'll tell you where the cutting edge of this is. But anyway, the simple answer to your question is that, Newton would pop out of Einstein. If you have Einstein, you can work your way back to Newton.
Okay, thank you.
One last question. Anyone in the audience? Okay, one over here.
Question, all of your roadmaps that you showed with the Feynman diagram assume that the dark matter particles are weakly interacting. Is there any reason to believe that they are interacting at all with normal matter, or is this just a case of the drunk looking under the light standard for his keys?
Yeah, that's a really good question. And that kind of brings to mind other cases like the sterile neutrinos. Like are there families of neutrinos that we just don't interact at all, so there's no possible way to detect them. So there are reasons to think why there might be dark matter that interacts. And it partly has to do with how the standard model is set up, and this is why they're looking for. This is why there's hope that the Large Hadron Collider will find something. Whether or not it's dark matter is one question, but there will be phenomena. So in a way, the way the masses of the existing particles cluster, it's kind of peculiar unless there are other possible particles that are kind of explaining their distribution. I'm not explaining this very well, but there are there are a number of models that kind of depend on there being something else. So those are sort of the clues. But I don't think it's ruled out that you could have something that is not that is completely uninteracting. But so we may be driven to that conclusion if none of these roads lead us to anywhere. One theory that I thought was very attractive was this idea. Here's a completely different approach. Imagine if you have parallel universes, many, many, many parallel universes, and each of them are infinite. And you sort of imagine it this way. Imagine if the universe is like an infinite sheet of paper. So it goes on forever. But a millimeter away from it is another infinite sheet of paper, and they stack and stack and stack and stack. So you could imagine, like the matter in one, if gravity could somehow be felt between universes, so you'd have to imagine a theory of gravity where gravity can sort of cross between universes. Like maybe the matter in our universe is being attracted by the matter in many other universes. And this is sort of what we experience as dark matter. It's just the pull of other matter in other universes, and they're all clumping together. That was an interesting thing. I explored that theory years ago when I was at Discovery Channel with the piece. I know that since then, that has fallen into disfavor for other reasons. But you kind of see these interesting explanations, and people play with them for a while, and then they find the limits of those explanations, and they kind of move on. But you're right in the sense, of like looking for the keys around the lamppost, that if there's some parameter space that can be searched, we might as well search it. So that would be the experimental physicist's response.
Okay. Thank you, Ivan. Thank you.
Thank you. Thank you. I'm going to express my appreciation by not hitting the microphone again and holding my hands together and saying thank you very much.
Okay, we're gonna have a break just in a moment here. I just wanted to say a couple of things about, for those of you who are new to who are here for the first time tonight. We are the Ottawa Center of the RASC. It's one of, as I mentioned earlier, 28 amateur astronomy centers across Canada. We have a number of benefits and membership here. Just real quick, if you become a member, and I'll talk about price in a second here. We obviously don't push membership, but I'd like you to make aware of it. We have a telescope loan library. We have an astronomy book library. We have an observatory, which is open and available to members. So you can sign out telescopes, much like you can sign out books. With your membership, you get Sky News magazine, and actually, now many of you know it's now owned by the RASC. An observer's handbook and other literature as well. Membership, a regular membership is $75. As a family membership is a reduced rate. If you wish to sign up, it's you go to the rasc.ca website, and it'll walk you through there. But I'm happy to talk more about membership. Let's go on. So up next is Al Scott. He's going to give a 10-minute astronomy news update on the latest in astronomy in the world of astronomy. Al.
Thank you, Mike. So, today's astronomy news is something that's been in the news. Some of you may have heard of it. And it's in regards to the Kepler space mission. Now, I spoke about Kepler maybe a year ago when I announced that Kepler was dead. And this was news because it was the Kepler Space Observatory, not Kepler the person. And the problem was the spacecraft had lost a couple of its momentum wheels and it couldn't stabilize its pointing. Now Kepler looks at stars, measures their brightness over long periods of time, and looks for tiny fluctuations in the brightness when planets around those stars slightly dim the light. So what they've done is they found a way to, there's a few different directions they can point where they can still keep it stable even with just 2 of the 4 momentum wheels. So they've actually been able to continue the mission in a limited way. And so this talk is about Kepler. And in fact, it's regarding Kepler and the search for extraterrestrial intelligence, which has come into the news recently. Kepler has done more, I think, for our understanding of the possibility of life in the universe than any other mission, in that it's actually given us one of the terms from the famous Drake equation to high accuracy. It's telling us how many planets there are in the universe, something we didn't know before the Kepler mission. How frequent are planetary systems, and what kind of orbits are out there? How many planets are in habitable zones where liquid water could exist, where life could exist? So Kepler's already said a lot to us about the potential for life to emerge on other planets. But recently in the news, people have gone towards maybe the type 1 of discoveries that Ivan was talking about. They've postulated that maybe Kepler would be a good way to search for advanced civilizations that are able to build large structures like the ones that Freeman Dyson theorized, the Dyson sphere, for example. As civilizations become more complex, they should be taking advantage of more of the resources of their parent star, and one way to do this is to build giant solar panels and obscure more and more of your star. And Kepler is the perfect tool to look for these advanced civilizations, looking at hundreds of thousands of stars. So Kepler, looking at these hundreds of thousands of stars for several years on end, looking for odd blips of planets. If there are alien civilizations out there building megastructures to capture the light from their stars, this would be an ideal way to find them. The difficulty is in providing the extraordinary evidence that would be necessary to make such a claim. Typically, planetary occultations obscure a fraction of a percent of the star's light for a few hours at a time, maybe a day, and in a repeating pattern year after year on its orbit. We've seen signatures of many planets, we've seen signatures of oscillating stars, we've seen binaries, we've seen ringed planets with symmetric obscurations of their stars. In 2005, kind of maybe a tongue-in-cheek paper by a guy named Luke Arnold suggested that advanced civilizations could use orbiting louvered solar cell rays not only as an energy source, but a low baud rate communication system to communicate to other civilizations. And you can see a picture in the bottom of this frame. Perhaps objects with Saturn-like cross-sections would be positioned to occult the starlight in prime number ratios on subsequent orbits. For example, 1, 2, 3, 5 that you see here. So this was from his paper in 2005. This is a light curve from a star, KIC 12557548, one of the ones looked at by Kepler, that has a pattern quite reminiscent of this. It's very odd. It's a repeating pattern. Something is orbiting this star and is occulting between 1 and 6 times the amount of light, seemingly in a random pattern on subsequent orbits. This is bizarre. What could it be? There was in the news very recently a plausible natural explanation for this. Perhaps a Mercury-sized object close to the star is breaking up and evaporating with a cometary cloud behind it that has turbulence that's generating highly variable opacity in the starlight. We don't really know. Until someone can either decode this as some type of interstellar Morse code, or someone can get a more exact observation of this system to tell whether or not this is actually happening, nobody really knows. It's possible this is a signal from some other civilization. Another one that was very recently come to the fore was a paper called Where's the Flux? The WTF star, published by the Planet Hunters. This is a group of just amateurs looking through the Kepler data online for oddities, and they found this light curve. This maybe doesn't come through as well, but there's a dip here, there's a dip here. This one goes down to about 15% of the star, and then there's a whole bunch of dips here. This one actually obscures 20% of the light of the star. They're aperiodic. This is a seemingly normal F-type star in any other way, but 1.5 times the mass of our sun, about 1,500 light years away. It's at a decent distance, so you can't really see it with the naked eye. It's a 12th magnitude star if you were interested in looking for it. But what could possibly be causing this pattern of obscuration? This star, what they found, is unique among all the hundreds of thousands of stars looked at by Kepler. Nothing else has a pattern like this. This pattern might not be surprising if the star was young with a gassy, dusty protoplanetary disk, but astronomers have looked at the infrared signature from this planet, this star, and there's no heat signature of a disk. There's no no significant quantities of dust in the system that would be reminiscent of a disk or the aftermath of a large collision. That being said, a run-of-the-mill alien solar collector would also put out a lot of infrared, unless they're extremely efficient. The best explanation that the astronomers have been able to come up with so far is that we've been lucky enough to see the breakup of either a Earth-Moon planetary system or a family of comets as they are coming into the inner solar system of this planet. And in fact, you can see that this, in high resolution, they found that there is a star that has passed nearby recently. So it's possible that this star has disrupted a family of comets and caused this to happen. In which case, we are extremely lucky to see an extremely rare event. And we should keep watching this to look for the gaseous absorption lines that should appear from the gas of this disrupting family of comets, or maybe look for the infrared signature of an expanding explosion from planets. Either of these follow-on observations should be able to detect evidence. Or it's just possible that this is some sort of strange alien megastructure that we haven't figured out. Of course, as I say, extraordinary claims require extraordinary evidence. The beauty of this is that anyone can do this science. Anyone can access the Kepler data online and download for free all of the data, which I did here for the WTF star, and plotted a few of these obscuration events. The star shows a 0.88 day oscillation in its brightness, which they believe is the rotation period of the star. You can see sunspots, for example, rotating every 0.88 days. They've also found, by looking at the time series over a long window, they found there's some sort of a 20-day pattern in the data that they can't decipher. They're not sure what it is, and they're not sure if it's a real pattern or just an artifact. However, by looking at some of these larger occultation events and plotting them up here, I found, I went one back. I found that there's about a 24-day repeat. These three events all looked kind of similar to me, so I plotted them up. There's 24 days between this one and this one, 48 days between this one and this one. So I then looked for other occultations in a 24-day period, and I found this one, which falls directly in between these two, and this one, which is several orbits out in the other direction. And these two are actually quite similar as well in approach. And you can see that if there was a pattern of solar panels orbiting the sun with louvers, they seem to fall on roughly the same frequency of delay between them. Of course, on a 24-day period, this is a 26 million kilometer radius orbit, so every day something would be moving about 7 million kilometers along its orbit. So this would have to be something very big to be on a 24-day pattern. And what you actually see when you look at the spacing between these subsequent peaks, that's about 0.88 days. It's about the same period as the star's rotation. So what could be happening is some sort of oscillation of the star or some sort of sunspot phenomenon that's obscuring huge fractions of the star. And then maybe a pulsation of the star is happening on this 24-day period. Nobody really knows, but the beauty of this is that you can all go online, look at the data, look for patterns yourself, and maybe discover an alien civilization. So that's all I have to say. Thank you.
Thank you all. If anyone has any questions for Al, you can feel free to speak to him after the meeting. Up next is Dave Chisholm, who's going to give a brief overview of what to expect to see in the night sky in November.
Okay. Good evening. Hopefully I'll get these buttons right here. So let's look at the skies for November. First of all, looking at the moon chart here, obviously the yellow is today. On the 25th of November, we will have a full moon. We also happen to have a full moon on Christmas Day as well. So next month it'll be on the 25th as well. The Leonid's meteor shower peaks on the 17th or to the 18th. And it's not a huge meteor shower. It's 15 meteors per hour in the year 2034. If you're around then, they're in the hundreds. So you got to wait till then. So we're in a bit of a lull when it comes to that. And the first quarter moon will set shortly after midnight, leaving fairly dark skies where there could be a good show. Best viewing will be from a dark location after midnight, and meteors will radiate from the constellation Leo, but can appear anywhere in the sky. This is an exciting comet that is going to start to make its appearance on November the 25th, and it will be almost right over Arcturus on New Year's Eve. So this is something for the challenge for some of our astrophotographers to see if they can capture this comet, but it starts become visible at the end of this month. In terms of the planets, Mercury is out during the daylight, so it is not visible. Venus is visible early in the morning, rising at 2, and as is Mars. Jupiter is now visible early in the morning. Saturn is not visible, it's rising, oops, I gotta keep pushing the button. Saturn is not visible, it's rising during the daylight hours. Uranus and Neptune are both visible all month. The International Space Station best viewing date is November the 10th, and it exits the shadow at 69 degrees, and here's a quick picture of the trajectory for this. This, if you ever want to find out when the International Space Station is crossing, go to the Heavens Above website. It is great to do these type of calculations. Sorry. And just make sure you set your destination properly. At one point, I couldn't figure out why it wasn't working, and I was off the coast of Africa. So make sure you set your home destination properly. And I'll leave you with this little cartoon at the end here.
Steve, you're up next.
Oh, and I'm up next. So keep on moving. Okay, so tonight I'd like to briefly share with you my adventure this last August when the Chisholm family gathered at the Algonquin Radio Observatory for a family reunion. So why gather at a radio observatory for a family reunion? Well, my father, Dr. Robin Chisholm, was part of a pioneering team of Canadian radio astronomers who were the first in the world to prove the concept of very long baseline interferometry, or VLBI for short. This is a picture of my dad standing in the dish of the Parkes radio telescope in Australia in the mid-60s. Unfortunately, he passed away suddenly about a year after the VLBI discovery. None of his children or his wife had visited the Algonquin Radio Observatory, and so we decided as a family to visit the location where he spent a significant amount of time doing his research work. Radio astronomy complements the optical astronomy we're very familiar with. It can provide insights into the universe that optics just can't pick up. And here's an example of an optical image on the left and a radio image on the right. Very long baseline interferometry, or VLBI, is the use of 2 or more radio telescopes spaced apart with their signals synchronized so that a sharper radio image can be obtained. The further the distance, the better the resolution. On April 17th, in 1967, a team of Canadian scientists were the first in the world to use VLBI between the Algonquin Radio Observatory and the Dominion Radio Astrophysical Observatory in Penticton, BC, a distance of 3,074 kilometers. You can see where the 2 radio telescopes are there, and we beat the Americans by about a month. These next 2 images give a graphical representation of how VLBI can enhance radio imaging. In the first image, the scopes are 60 meters apart with a resulting image in the upper right. The next screen is with the scopes about 1 kilometer apart. So you can see how much clearer the image is. So this is the Algonquin Radio Observatory. It's the 3rd largest radio telescope in North America and the largest in Canada. The dish is 46 meters across. The next largest radio telescope in Canada is the Dominion Radio Astrophysical Observatory in Penticton, BC, at 26 meters. It was built in 1965 by the National Research Council and is located in a remote location so as to be away from human-made radio interferences. In 1987, the Algonquin Radio Observatory was turned over to Natural Resources Canada, who ran it until 2005, at which point it was about to be decommissioned For the last years of its life, up until 2005, it had been poorly maintained. A private company, Thoth Technology, approached the government and arranged a long-term lease of the facility, and has since brought the radio telescope and the site accommodations back up to standard. Significant expenses were involved in replacing the bearings on the telescope, which had been destroyed by age and improper use. If you were here last December, I showed you a short video from the Discovery Channel on that particular piece of work. So where is the observatory? The Algonquin Radio Observatory is located on the edge of Lake Traverse in the north portion of Algonquin Park. It's accessible from the Sand Lake Gate entrance of the park near Pembroke. It is a 75-kilometer drive from the park boundary to the facility. It's about a 3.5-hour drive from Ottawa. Visits to the facility are by appointment only. Thoth Technology does take bookings for visitors through their website, arocanada.com. The lodge has 14 bedrooms to accommodate visitors, and meals are fully catered. There's no facility there for bringing your own food. Even though I was going north, this is not a picture from last August. I forgot to take a picture of the lodge, and this is my dad's picture from February 1965. It hasn't changed much on the outside since then. Ben, Carolyn, and Catherine from Thoth Technologies were very gracious hosts. If you plan on visiting, you'll be booking through Carolyn. You may have seen Ben and Carolyn in the news last August as they discussed Ben's patent on the space elevator. I booked our accommodations 9 months in advance, and the current rate is $285 per person single, plus you have to pay for your provincial park vehicle permit, which is about $15 to $20 per day. I just was exchanging emails with an RASC member from Toronto, and they've already booked their next visit to the radio telescope for Labor Day in 2016. The lodge is located on the west end of Lake Traverse. It has a nice sandy beach with canoes and kayaks which you can borrow. The sleeping accommodations are very comfortable, and the food was amazing. There's no cell phone coverage in this area of the park, and there's limited Wi-Fi availability at the lodge. The radio telescope and control rooms are located about 1 kilometer away on the other side of Xray Road. We have picked the weekend closest to the Perseid meteor shower, and so we were joined by members of the Toronto RASC on that weekend. Because of our past association with the telescope, our host graciously offered us and the members of the Toronto RASC a, quote, platinum tour of the radio telescope. After a tour of the control room, the next step was to level the telescope, and if we can set that in motion, please. And this video stop motion animation was taken by Stephen McKinney of the Toronto RASC. Once inside, we had to don hard hats as we climbed 3 stories to the outside ledge. This is my son Robbie looking over the ledge. We then climbed another 3 stories of ladders and catwalks to exit onto the dish. My mom was officially the oldest known person to climb into the dish at 83 years old, and she's the second person from the right there. This is going to be our family Christmas picture. On the Saturday night, we had clear skies and more mosquitoes than stars. I tried to get my telescope out, and I was getting eaten alive. So luckily, the folks from the RASC in Toronto, in particular Stephen McKinney, were graciously shared me some of the images they took. And here's an image of the disk, and you can see the Perseid meter just going through there on the left-hand side of the dish. And the skies are just amazing up there. Not only did we get dark skies, but we were also blessed by the northern lights in the early evening. This was taken from the beachfront on Lake Traverse. And we'll put this in motion now. Hopefully. There we go. As people drive into the dish at night, their headlights light up the surface of the radio telescope, much to the chagrin of those who are imaging. Those are probably my headlights. Oh well. I'd encourage any of you who are looking for a unique location to do your observations or unique weekend away to consider the Algonquin Radio Observatory. It was an awesome experience. Thank you.
Again, if anyone has any questions for Dave after the break, after the meeting, please. Okay, so the next part of the meeting is something very special here as we wind down here. I mentioned that some of the finest astro images and videos of the air you'll see tonight. Let's get started. So Andre Paquette, I'm very pleased that Andre, you're here. Perfect. He's got something very special to share, as every one of these presenters do.
Can we turn down the house lights, please?
This is what I was going to say. Do you need lights?
I don't know.
I'll give you a...
Can I drive with this?
Yes, you can.
Just which button?
The right button.
Okay, thank you.
If you need lights, you can use that.
Okay, thanks. Hi folks, my name's Andre Paquette and I'm here to share a few astro photos with you. I live out in the West End in near Carp, Ontario, and I use a 14-inch corrected SCT. And in September, I just got back my big camera from repair, and I was extremely pleased to have a couple of weeks of decent weather at that time, so I started taking some images. In that setup, by the way, I get about half a degree by half a degree of field of view that's fairly high resolution, and it's a fairly flat field, and so the images turn out quite well. So there's the first one. This is the Cocoon Nebula in Cygnus, IC 5146. I haven't seen these on a big screen before, so I'm checking it out too. I'll say a little bit about it. The pink is hydrogen. The blue is on the right is a small reflection nebula. The light scatters and makes it blue. And there's a lot of dust in here as well. On a subsequent night, I took an image of the Bubble Nebula, which is this guy. And this is false color. So this is the Hubble palette, where red is sulfur emissions, green is hydrogen emissions, and blue is oxygen emissions. And the moon was out, and so I said, okay, fine, we'll deal with that and do some narrowband imaging. And this is a zoom in of that. Thanks.
Holy freaking awesome.
Thanks. I was pretty pleased. So these were the two that I took in September, and this one's earlier this year. So this is the Pickering's Triangle. It's also in Cygnus. Same field of view, half a degree by half a degree. In the previous two images, there was 3 hours per channel. In this one, there's 1 hour per channel. And this is a true color image. There's no luminance, it's just RGB. In this one, the pink is a combination of gases like hydrogen and sulfur, and the light blue is oxygen. On to the next. This is one I took quite a while ago, NGC 891, Edge-on Spiral Galaxy. This has a lot more exposure in it. I think it's about between 4 and 5.5 hours per channel. This is from earlier this year, Comet C 2014 Lovejoy. This is in a different imaging configuration. Usually I use a prime focus configuration, which is f11. This is crazy hyperstar configuration for those of you who know what that is, and that's where you put the camera out on the front of the telescope in order to get f2 or f1.9 instead of f11. And the camera in this case is a Nightscape 8300. And this is a bit of a crazy image. This isn't my telescope. This is it's the same camera, but this is a planewave 20-inch telescope in New Mexico. Why would you take a picture of the moon with a 20-inch telescope? It was, well, I guess, but this is actually with narrowband filters. So this is a false color image with hydrogen and oxygen as the two channels, and then combined to produce a quasi-true color image, and it really brings out the differences in the seas and such in the moon. And there is a lot of detail. It's very sharp. When you use narrow filters, you often get a very sharp result. And that's not stacked. Those are two images. No, there was no statistical anything there. And that's all.
So Andre, yeah, just look again at this. I love this. I love this setup here. The screen, the projector. It's just this makes this place just perfect. It's something to see, and I'm very pleased with the auditorium here. Andre, we're going to be calling on you more. Okay, next up is Taras.
Hi, I'm Taras Rabarsky. I am new to RASC. It's only my first year, and I'm using 8-inch Schmidt cast for my photography, usually in prime focal mode. But for planetary images, I'm using lenses with, so the scope itself is 2000 millimeters and the lens is 5. So it's kind of 400 times magnification. And this is Venus. It's, well, there is not much interesting to see because, as you know, it's covered with thick clouds, sulfuric color, and the global warming ran a really bad way on that planet. So you really can see that it's crescent shape. It changes the shape depending on the phases of the moon. Next slide. Actually, I think it's this one.
Right button.
Yeah, this is obviously Mars. This picture was taken a year ago, though Mars was pretty high up in the skies in April, and I was able to take this picture right from my backyard. It's a stack. Actually, most of them are a stack of about 8 to 1,000 images taken with the video. So I manually, sometimes with the help of some application, pick up to 800, 1,000 best frames and stack them with 2 different applications, Registack and then Linkios. And then those 2 best ones are being, again, stacked together to get a better image. And this is, again, a bit later in 2014. This is Mars, a little bit, you can see the polar cap on the top, rather, a bit on the left. So Jupiter, well, it's easy target. It's a bit oblate. It rotates very fast, rapidly. It's one rotation in about 10 hours, and you can see the red spot. I was lucky to take a picture of a red spot that night. It's 2 to 3 sides of the moon, rapidly rotating as well, and it's, I guess, favorite for many of us. It's kind of a little bit of time lapse. So the previous picture was the difference about 29 minutes between the shots, while these 2, or rather 4 frames, sorry, it's within 20 minutes. I picked manually better frames out of what can be retrieved out of those pictures. Now, this is, I think it's a bit kind of over contrast, but you can see a little bit of like filaments and jets of gases on this picture. So in those bright areas, under normal contrast, you see the bluish gases emitting from the weather belts. Saturn, this is taken from Mill of Kingtail early this year in May, and Saturn was pretty low this year. It's close to the horizon, so it's not the best in terms of the details. But you can a little bit see also the weather belts. This is Fred Lossing Observatory scope. I used just adapter to put my camera inside, and you can see the Tycho crater on the moon. Pretty much, I guess, happy with the details. You can see some details where the crater impacts were. this year's September 27th lunar eclipse. So this was taken with, I think this is a combination of 5 shots superimposed to get rid of the noise. Thank you.
Thank you, Chris, for sharing your images. Next up is Raymond.
Thank you, Michel. Thank you, Wayne. Bonsoir, good evening. This is a photo that I took just outside the door of my backyard before I went to work. It was taken at about 6:30 in the morning. It's on a Nikon D700 on a tripod. Shutter was half a second, f4, ISO 2500 at a 70 millimeter focal length. On the right. And this one is about 3 days later. I took that one over at the Petrie Island, and also was on my Nikon D700 on a tripod, 8 seconds at f6.3, ISO 1600, 50 millimeter, at about 6 o'clock in the morning on the 31st. And this screen is really good to see this stuff, really is. Merci, thank you.
Thank you, Raymond. Eric, what do you got for us this month, Eric?
Hi there. This is Burns Lake, which is just north of Teeples Hill, which I like to go to lately. And I've been scoping out this site for quite a while now, because I had wanted to capture auroras in a time lapse over a lake. So if we could play this here, please. So this video spans 3 hours, just over 3 hours, and each exposure lasted 5 seconds. Now the funny thing is that I had set up on my tripod and had figured, well, it's dying down, so I'll pack up. I was ready to go home, and at the beginning of this time-lapse shot, I decided to set back up. So instead of setting it up like I thought I was going to be there all night, I set it up with the tripod adapter covering the battery compartment. And right at about this point I realized, oh no, the battery's going to run out. The problem with time-lapse is that if you take the battery out, or if you have to take the rig apart to put a battery back in, and you move the camera angle ever so slightly, you can't really get it to continue later on in the video. So in the few minutes that I was taking other pictures or so, it started to really flare up, and I decided, okay, well, I might as well take a few more images and try to put it together and just see if I can get it to work afterwards. So I've got a second video here, and it fizzles out pretty quick, but if we could play part 2 here, please. So the reason why we're playing it in a separate player here is just because in PowerPoint, the way I put together the video, it was choppy, and so for now, so that it's not choppy, eventually we're going to figure out how to get it to play in PowerPoint. But and you know, so as I'm driving home, it actually kept on getting brighter and brighter and brighter, and I'm going through Renfrew, looking up through light polluted skies in Renfrew, thinking, you know. But so that was that. A week later, I decided to go back, try some more photography, and this time I decided to bring my dynamic perception stage R unit, which is a unit that rotates the camera as I'm taking the time lapse. So it'll do a shoot, move, shoot all night long. All these images are 15 seconds long, but I took the ISO down. The previous one I took the images at ISO 6400 because I didn't want to have too much motion of the auroras shot to shot, because it it would blur. So this one, though, I wanted to bring out more of the Milky Way. And thanks. Thank you. So it only became apparent when I put the video together that the reason why I wasn't able to make the Milky Way pop out more than I expected was because if you'll notice at the bottom right, there's auroras happening again. So I couldn't see that in the individual frame-to-frame, shots. It's only when I put it together. So this shot at the beginning was facing more towards Kingston, and it finishes off pointing towards Pembroke. That's the light pollution reflecting off the clouds from Pembroke. So, thank you.
Outstanding, Eric. Definitely, we want you to come every month. Okay. All right. Next up is Paul Clowerger, and folks, we're almost done. I would say less than 10 minutes. Paul.
Well, hi there, everybody. As you know, we had a beautiful lunar eclipse. For those of you that didn't get clouded over for it, I showed you some images last month. In the subsequent time, I've had a bit of a chance to. I went back and processed one of my better still images there, and I also went back to the same piece of sky and shot it 10 days later without the moon in the sky, because I wanted to get the background stars in that piece of the heavens and put the two together. So basically, that's what the sky looked like behind the lunar eclipse as it was happening. One of the reasons I wanted to show you this, and some of the other shots that I'm showing you tonight, is that I'm using a rig. For those of you that are into equipment at all, I've been testing the new Skywatcher Star Adventurer rig, which is a very small, portable, very versatile little rig that does similar stuff to what Eric was talking about with the rotations and time-lapse configuration. So most of these shots were taken with that rig, including this one. I just had my 70mm Apo sitting on that little rig, and it's highly portable. It just sits on a tripod and can take some very accurate shots. So we were lucky to have some good sky where we went down by the St. Lawrence to get the lunar eclipse. And then a week later, as Eric has already showed you, we had yet another unscheduled event, and that was the aurora of October 7th and 8th. So next one, please. I've got a few stills from that night, and like Eric, I also did time lapse. In fact, Eric and I were sort of talking back and forth that night, so I can vouch for his frustration when he told me his battery was running out. There was explicit deletives on my text message there, but he was about 60 or 70 kilometers north of where I am as the crow flies. So we were just texting back and forth and saying, oh, there's a 40-degree high ray in the Big Dipper and such there. So we could sort of coordinate our efforts there. So that was a rather interesting evening. But a couple of stills here for you. The next one there as well. This was a really interesting aurora. In fact, you'll see from the time lapses, you already got a feel from it from Eric's, that this aurora changed character a lot. It's been rare that I've seen an aurora change its character so dramatically in the span of a few hours. You had times like this where there were very pronounced rays, and they were all in motion, like they were all moving. It was obvious that there was a vortex going on, as has been photographed from space. These vortices tend to be several hundred kilometers in diameter, and interestingly, what you'll see when I run my time lapse there. This is unfortunately, I think, the part that you got a little bit pooched on with your battery there, Eric, but you can see that the vortex, it almost seems to be counter-rotating, like energy field within an energy field. Anyway, it was very, very dramatic and very changing. Next still there, so you can see that was later on. Again, the character had changed, it had become much more diffuse at the bottom, but with very tall rays. So when we run the time lapse, what I shot here was, again, with the Star Adventurer mount, a series of about 700 images spanning 5 hours and 44 minutes. So the time lapse is sped up by a factor of about 300 over real time, and you'll see how it changes. It begins with the rays, then it becomes very quiet for a bit. And then it flares at the bottom. I think you saw that with some of Eric's there, where it gets very green and flary, and then the character just changes, and you can see the vortices, including what I call towards the end there, you'll notice it here. I'll just point it out before we run the video there, but you'll see a little, what I call a Tasmanian energy devil developing near the middle. And it just kind of rocks along the horizon like this, and it changes course, and it's obviously going around the back side of the vortex as it peters out there. So quite an interesting evening of aurora shooting. It wasn't much to look at, I found. I mean, it certainly had its moments visually where you could see, you could see where these bright areas were forming, but it wasn't like spectacular visually, but the cameras really picked it up. And so it was very rewarding like that. So the next one. Yeah, so that's the beginning sequence. So you'll notice too that in this time lapse, this mount is very new for me. So I've been experimenting. There are jumps and hiccups in it, and times where I would change course to follow the motion. So yeah, rather interesting night, and even a couple days ago, we had yet another apparition of the aurora. The conditions between the Earth and the Sun are very conducive at the moment to auroras, so we may yet see more. The last image I have for you, also shot with this Star Adventurer mount. I'm finding this a really interesting little rig. This is just with my 60DA and a 200mm telephoto lens. No auto guiding on this. Combination of broadband and narrowband imaging that I've read to get the hydrogen alpha. But you can see the jellyfish nebula there, the monkey head down at the bottom left, and M35 down at the bottom right there. So a nice little clustering of objects, perfect for a 200mm field up at near the foot of Gemini, just north of Orion. And that's all I have for you. Enjoy your weekend.
And I have two quick images for 10 seconds. During the lunar eclipse, how many people have a plane going in front of the moon during a lunar eclipse? I bought a lottery ticket next day, didn't win. And next slide.
It was the wrong plane.
Wrong plane, that's why. Here we have one of the many conjunctions. It was on November 4th, Jupiter up on top, Venus in the middle, and Mars just above that. But the thing was that we had heavy fog in South Mountain, so it made these beautiful orbs around it. That's it for me. Thanks for everybody that came for the first time. Hope to see you again next month. And everybody.
Thank you, Gary. Now you know what I mean when I say that we've got some fine astro imagers here, and we should be better represented in the calendars here. All right, so folks, let me wrap up. Estelle's, our librarian's pick of the month is this book here. Next meeting is December the 4th. It's going to be a different meeting. Instead of having speakers, we're going to have, I think I mentioned before, a sort of like a science fair, a lot of booths set up. Members will share some of their innovations and their tips and techniques. We're going to be set up either here or in the auditorium. Haven't figured that out yet. But already I've had about somewhere between 10 and 15 people who have asked to display their ideas. So it'll be a great opportunity for collaboration, open to everyone. I'm just going to move forward. We do actually have our meetings that are posted on the web. These links will take you to YouTube. Eric posts them in about 2 weeks. You can look back at some really fine meetings. Good attendance tonight. Thank you to thank you to everyone who presented, and to the presenters who put so much time and effort. Ivan, thank you so much for coming. It was a pleasure having you. We have a after-meeting social event at Grace O'Malley's. Okay, this is actually, we're trying out a different place this month. This is at Ogilvy and Aviation Parkway. If you go down Aviation Parkway, you turn right. I think it's onto Ogilvy. It's the first building on the right, I think. Okay, so you can't miss it as you go west.
Watch me try.
Okay, so now, folks, I'm going to call an end to the meeting. Thank you so much. I'm going to call out the door prizes right now. You don't have to stay for this, okay? But each of you should have a ticket. Martha's going to help me here. Pull the tickets. And for those of you on the internet, thanks for joining us. I know we're having some people from the West. Always a pleasure to have you. So thank you, everyone. And we'll just call it the door prizes.